All right, good evening, everyone. Welcome back to Math 261. It's February 21st. Reminder that 1.7 and 1.8 homeworks are due tonight. We will get all the way through 3.1. We'll actually start 3.2 as well tonight, but we definitely will not finish that section. So 2.2, 2.3, and 3.1, those are all going to be due on the 28th. The most important reminder is your test on chapter 1 is currently available in my math lab. I'm actually giving you through the 24th. I'm just going to give you an extra day for this first one while we're kind of getting used to everything. This will be an unproctored exam, but please understand that there will be a proctored My Math Lab exam, at least 2 of them during this semester. The final will definitely be proctored, and then either test 2 or test 3, one of those will be proctored, which means you will need to have a webcam up to record yourself taking the test, or your cell phone up to record yourself taking the test. So one of those 2 options will be mandatory for, again, definitely the final exam, and either test 2 or test 3. We'll figure out which one as the semester progresses, as we get a little closer. But that first test is due on the 24th. You've got a review right after the chapter, right after 1.8's homework that I had suggested everyone complete. So you've got 3 days, well, technically 4 days to complete that. It has to be done in one attempt. You have 2 hours, 20 questions, no notes, no books, no calculators. You must show your work with pencil and paper or whiteboard or whatever you're using. Take pictures of it, submit an image file, a PDF, whatever in Canvas. That link is currently available. When you log into Canvas, if you scroll down just below where all the lecture videos are, you should see something that says something along the lines of submit test 1 work here. If you do not submit work, I do reserve the right to give you a 0. This is a calculus class. You're going to need to show some level of work. If you think you deserve any partial credit, you can email me, preferably through Canvas, but I'll take it either way. Make sure that you say this is Math 261 and say which questions you think you need partial credit on. And then I'll look over them. Give me some time. I won't do any of the partial credit until everybody has submitted their exams. So if you email me on the 22nd, I at least won't get to it until the 24th or 25th. And admittedly, I am going out of town this weekend, and I'm not going to have access to the internet probably. Well, I mean, I might, but I'm not going to have my laptop with me. So I'm not going to be looking over any tests until Monday, most likely after the 25th. So it might take you a week if you're doing your test early. But besides that, let's pick up where we left off. We had talked about the chain rule. We had talked about the chain rule using logarithms, and we're going to make a little more of a generic statement / formula with that. First things first.
Chain rule has to be done even with these simple problems because you can make mistakes otherwise, especially with the more complicated ones. So let's lay out what the chain rule for natural logs is. So we can skip labeling the insides and the outsides for this because, again, it's a pretty common occurrence. So the derivative of the natural log of a function. So in other words, the natural log of something besides just an x. So this could be a 5x, it could be an x squared, it could be a million x minus 7. What it turns out to be is the derivative of the inside divided by the inside. This is fascinating. And the previous example does actually demonstrate that. This 5 was the derivative of the inside, and the 5 ends up in the top. The bottom, the 5x, was the original inside. Again, the top, the 5, that's the derivative of the inside, which again, I wrote it to the side, but that can be considered to be in the top. The bottom, the 5x, was the original inside. So that's what this says. The derivative of the inside divided by the inside. This is equal to, again, the derivative of the inside divided by the inside. That's using our words. This is using our math. This is using our words. So let's try using that on a more complicated problem. So for example 2, let's find f prime of x, and you know what? Let's put it down here. I almost wish there were no page breaks the way I'm doing things. And this is going to be f of x, and this is a. F of x equals the natural log of x to the third plus 2 in parentheses. Definitely getting into the more complicated functions. Now, you can still apply the chain rule as we did with the previous example. You can label the inside, you can label the outside, you can label the derivative of the inside, the derivative of the outside, and do all that appropriate stuff. Or instead, again, because we see this so much, so very, very, very much, you can just say, let me memorize this extra formula. The derivative of the natural log of something else, let's call this the inside, is the derivative of the inside divided by the inside. Get these in order. If you swap them, it's wrong. If you do the inside divided by its derivative, wrong. It's the derivative of the inside divided by the inside. So I'm just I will label what the inside is. Oops, wrong color. That's x cubed plus 2. I'll even write out what the derivative of the inside is, which would be 3x squared. The derivative of x cubed is 3x squared. The derivative of 2 is nothing. That's what, the 100th time we've done the power rule together, probably? So that says f prime of x is equal to the derivative of the inside divided by the inside. The derivative of the inside is the 3x squared divided by. The actual inside was the x cubed plus 2, and guess what? There's literally nothing we can do to that to simplify it. That's it. That's all we have to do now. We don't have to label the outside with some confusing substituted variable, whether we're using u or a different x. It's a lot nicer this way. The same reason we gave an abbreviated chain rule formula for exponentials with a base of e. But with just plain Jane polynomial and product and quotient functions, we can't label a general chain rule for every single thing like that. We'd have to memorize 5 million formulas. So we don't. Alrighty, another one, B. We'll do 2 more. F of x equals the natural log of x squared plus 5 raised to the 4th power. Now, I need you to note, this is not the natural log of x squared plus 5 raised to the 4th power. If you need to see extra brackets and things, it's really the natural log of x squared plus 5 in parentheses to the 4th power. In other words, the exponent of 4 is inside the natural log when written this way, not outside. That is a giant distinction, because if we had to do the problem that it's not, this would be a double chain rule, which we have done before and you can do, but that's not what this is. This is a single chain rule. So if you want to call the inside something, it's the x squared plus 5 all raised to the 4th power. Then the derivative of the inside, well, you got to chain rule this. So the derivative of the outside is going to be this. I'm going to do this a little quicker. It's 4 times the inside, and then drop the exponent by 1. This right here is the derivative of the outside, pretending that the inside was just an x. Again, this was the derivative of the outside times the derivative of the inside being the x squared plus 5. I will go back and show all the detail. I'm just showing a quicker way to do this thing. So this is me Everything that I'm scribbling out right now is what I'm calling the inside. I'm pretending like that's just a single x when I do my derivative of the outside. So I'm pretending that it was x to the fourth, and its derivative is 4x cubed. But then I got to do times the derivative of the inside. Well, the inside was x squared plus 5, which is a derivative of 2x. The derivative of the 5 is 0. Now that is really the 4 and the 2x can be multiplied to be 8x times x squared plus 5 raised to the third power. So we got our inside and we got our derivative of our inside. So that means we can write our f prime of x. It's just the ratio of those two things. It's the derivative of the inside divided by the inside. The derivative of the inside is what goes on the top. That's the 8x parentheses x squared plus 5 to the third. If you need to see that derivative, I'll do that at the end in more detail. Divided by the inside, that was the thing to the fourth power, the parentheses x squared plus 5 raised to the fourth. Now here's what's fascinating. You have like terms that can cancel. You have common factors, not like terms, common factors. X squared plus 5, x squared plus 5, so we can get rid of some of them. There's 3 in the top, there's 4 in the bottom, so we can cancel 3 of them. So we can get rid of 3 of the 4 in the bottom, which means there's 1 left over. We can get rid of all 3 in the top, which means there's 0 left over. So f prime of x is the 8x is still on the top. The parentheses is completely gone in the top, but you still have your x squared plus 5 in the bottom. So that one I think is fascinating because this exponent that was a 4 was completely irrelevant. It makes this chaining much more complicated when you do the derivatives this way. But after you get your derivative, the derivative of the inside over the derivative, over the inside, derivative of the inside over the inside, you end up canceling out almost all of them except for just a single one in the bottom. I'm going to show you, excuse me, I'm going to show you using a pre-calculus rule for logarithms why this works even without chaining anything. But before that, I said I would point this out in writing. Note, for x squared plus 5 raised to the fourth, its inside is x squared plus 5. Its outside would be that special x raised to the fourth power. Again, where that green x really represents the inside. So the derivative of the actual inside is 2x. The derivative of the outside would be the 4x cubed with that special x really representing the inside. So its derivative, let me just call it y prime, if I call that y. The derivative of the inside times the derivative of the outside. So that's 2x times the 4x cubed, but it's not really 4x cubed. It's that parentheses x squared plus 5 cubed. Which is really 8x times x squared plus 5 to the third. So that says what we got above, whether we do it a short way or a long way. But when you've done 20 or 30 or 40 chain rules, you should be able to get much more efficient with them when they're just a polynomial raised to a power. Practice makes perfect. If you do 5 of these, you're probably not going to feel comfortable on a test. If you do 30 of these, you're going to feel much more comfortable. That's why we tell you study this stuff for 8 to 9 hours a week outside of class. You include class time, that's 12 to 13 hours a week that you should be doing this. Okay. Before we move on to another example, I said I would show you another way to get this derivative without chaining it. This 4 right here doesn't need to be an exponent. So let's go back to pre-calculus. Back in pre-calc, you learned that the log of anything with an exponent, where the exponent's inside the log, can just be brought out as a coefficient. The exponent can be brought out as a coefficient. The exponent becomes a coefficient. This is only for logarithms. Any type of logarithm works, but it's only for logarithms. That's never true of anything else in the world. The exponent inside of a logarithm can become a coefficient outside of a logarithm. There's reasons that that works. We're not going to prove it. This was pre-calculus. You should still remember this. You could still need this at some point in this course. So let's go back to the original function, which was the natural log of x squared plus 5 to the fourth. Check this out. Using that rule, you can bring the exponent of a 4 out front to go 4 natural log of x squared plus 5. Now you can't do the same thing with this exponent. You can't do that with the 2 because the whole thing isn't being squared. It's just a single term. Well, guess what? Now that 4 is just a coefficient, makes this derivative a lot easier to take. It's just derivative of the inside divided by the inside. So f prime of x would be 4 times the derivative of the inside over the inside, which is 4 times the derivative of x squared plus 5 is 2x over the actual inside is x squared plus 5. The 4 times the 2x makes 8x over x squared plus 5. Same answer. Much easier that way, but if you don't remember that pre-calc rule, it wouldn't give you efficiency. Did you need that rule to do the calculus? No. Does it help you do it more efficiently? Yes. But at least that shows that the calculus that we did with all the extra chain rule stuff, it wasn't for naught. It actually works. It's nice when we can get an answer a separate way to say, yeah, okay, that's good. If it's right 2 different ways, it probably makes sense. All right. And that was B. So let's do C. Last problem for the section. F of x equals the natural log of x to the fourth plus 1, then a minus 4, that's an ugly 4, e to the x over 2 minus x. Multiple terms, so at least with the pluses and minuses, they don't affect each other for derivatives. But we gotta take a derivative of a logarithm with a fancy inside, so we're gonna need its particular chain rule. We gotta take the derivative of a fancy exponential, so we're gonna need its particular chain rule. And we got a derivative of a polynomial, so we need to know that in all its special cases. So for the first bit, for the natural log of x, its inside, sorry, the natural log, I didn't mean to say x. Its inside is the x to the fourth plus 1, and its derivative would then be 4x cubed, because the derivative of 1 is 0. I'll do this in a different color. For the exponential, the inside is the x over 2, and its derivative would be 1/2. X over 2 is a linear term. It's 1/2 times x. And the derivative of a linear term is its coefficient. We don't need any fancy stuff for the minus x part. So f prime of x equals, for the natural log part, that formula was the derivative of the inside divided by the inside. The derivative of the inside divided by the inside. The derivative of the inside divided by the inside. So let's go back to our red. The derivative of the inside was the 4x to the third over the actual inside was the x to the fourth plus 1. Then the minus. That 4 is a coefficient, leave it alone. The exponential rule said that the derivative of an e to something fancy is the derivative of the inside times the original exponential. The derivative of the inside times the original exponential. So the derivative of the inside is that 1/2. So times 1/2, that's the derivative of the inside, times the original exponential, that's the e to the x over 2. Then minus the derivative of x is 1, so minus 1. Again, linear term, special case. Let's clean this up and write it all in the same color for sanity's sake. Nothing you can do to the first bit because the bottom's a binomial. Why did I say monomial? The 4 times 1/2 is 2, so that's minus 2e to the x over 2, and then a minus 1. That's all we can do. You can do this stuff with a product of an exponential and a logarithm. You can do it with quotients. Everything can be combined. With derivatives, any and everything can always be combined. It's just a matter of what the nature of the problem is, what they want to give you. All right. So that is it for chapter 2 for now. We will come back to it if we can at the end of the semester to talk about some more interesting topics, or if I find that we're on a really good pace before we get to integration, I would prefer to come back to this topic, but I usually can't gauge it at that point. Some semesters I've been able to come back to it, some I haven't. It really does just depend on how far we can get in the class. But the crazier topics I would rather save for the end. I want to make sure we can get the core concepts down. Because if you've got the core concepts down, if you then have to apply it into some 300 level economics class, they're going to give you the applications. You just got to know your calculus formulas and how to apply them. So you generally would see this stuff again in terms of applications, unless you just have a teacher who's going really quickly through stuff. I don't know. So that'll be it for chapter 2 temporarily. I hope that I can save this later. So what we get into now is chapter 3. And yes, we do have to keep moving forward. We can't waste time. Remember, test 2 is going to include several different chapters. It's going to be parts of chapter 2, parts of chapter 3. That should be it, just parts of chapter 2 and parts of 3. We don't need to talk about that too much for a while. So 3.1, using first derivatives, classify maximum, minimum values, sketching graphs. Ourselves lots of space. Okay, so we have now got a series of formulas for finding derivatives. We can find the derivatives of several different classes of functions. We know how to find derivatives, polynomials, using the power rule, products and quotients, composite functions, that was the chain rule, and then natural exponentials, and natural logs. And yes, I want my Oxford comma. I am an Oxford comma person. which some people probably say that makes me evil or something like that. I think it just means I like commas. So that's what we've done in chapter 2. We have learned, I'm sorry, chapter 1 and 2, chapters 1 and 2. In chapter 1, we picked up polynomials, product, quotient, and composite. Just that brief synopsis in chapter 2, we picked up the natural exponentials and natural logs. Once again, if this was a true calculus course, we would need a whole other series of derivatives. We would definitely need the general exponential and general logarithmic derivative. We would need derivatives of trigonometric functions. We would need derivatives of hyperbolic functions, which some pre-calc classes don't even get into what a hyperbolic function is, so that can be kind of jarring. And I'm not going to get into that because that's not what we talk about in here. So that's what we have so far. We are able to find derivatives of all the classes of functions that we need to be able to take derivatives of. So what we're going to start doing to expand this concept of calculus is some very deep graphical analysis. And you started doing graph analysis back in Math 161. We talked about finding maxima and minima just by having a graph and pointing and saying, hey, this is a max, this is a min. So back in pre-calc, you could make a graph or be given a graph and find its local extrema, which were the local maxima, local minima, which just means highest and lowest points in a region, by looking for peaks and valleys. So back in pre-calc 1, you got some graph. And it looks like this. And we could say that there is a local max right there and a local min right there. Those are our peaks of our hills and the bottoms of our valleys. We can't say they're absolute extrema, which would mean the highest and lowest values, because this curve goes up forever and it goes down forever. So there's lower and there's higher points. But what we're talking about here is you're imagining that you're only looking at the window right around here. So for any particular point, imagine you took your nose and you put it on that little blue dot right there. And when you look at that, you would see in the area around it, everything else is below it. So in that green little spot, let me zoom in. If you were to zoom into that spot, all you'll see is this. That's all you would see. And in that local region, in that small region, it is the highest point. But it doesn't say it's an absolute max, it just says it's a local max. Another word for local is relative, by the way, and I'll write all that out. The same thing would be said if you did that here. If I did it here, if I zoom in here, then the graph is just doing this. I don't see any peak or valley there. That's why we're only looking for sections for tops of hills or bottoms of valleys back in pre-calc 1, and then we just hope that we have those coordinates, either by plugging an x value into the function or whatnot. But that was us using visual aids. In calculus, our idea is not to necessarily look at this, but to find exactly where this is located by talking about how the slope changes. So in calculus, we find these not necessarily by just visual observation, but by discussing how the function is changing, because at these points, the change is very specific. Okay, So definitions, local extrema, aka relative extrema. Just in case you're pre-calc's rusty, a relative maximum, sorry if I'm saying a, let me pluralize it actually. Sorry for that. Relative maxima are the highest points in a small region. Relative minima are the lowest points in a small region. Again, when I say small, I mean very small. You imagine that you are taking your nose and you're putting it on a peak or a valley so that all you can see is just that teeny, teeny, teeny little section around it. You're putting on your blindfold, if you will. That was my knuckles popping. Bones and joints, which I'm sure you heard. So that's what we mean by local extrema or relative extrema. There can be multiple local maxima. There can be multiple local minima. So I don't want that highlighter green color anymore. So our curve could do something like this. And then it's got a whole bunch of different, I'll do in blue, the local maxima. And then in, let's go with orange, the minima. So minimum is singular, minima is plural. When you have that A at the end, that's plural. So there's 4 local maxima here and 3 local minima here. There is actually an absolute max, which means the highest of the highest points. And the way I've drawn it, it kind of looks like this one. But there is no absolute min because this graph points down in both directions. And we'll get into absolute extrema later, but not yet. So using calculus, what can we say all of these things have in common? Well, I'm hinting at what we should be thinking about. We should think about how they're changing. How are they changing at these peaks and valleys? So let's zoom in. Let's go back to the zoomed in feature of just some of these. Let's look at the first one originally. Oops, and I don't want to write. Let's zoom in on the first graph to the 2 peaks, the 2 extrema, excuse me, the peak and the valley. So the green one I'll keep as a green box. And then the other one I'll just do as a different colored box. Let's go with gray. So again, nose to the board. And you don't even have to zoom in though, but I just want to try and emphasize this. So we got our gray box. And in that region, the curve was doing this. And we are very interested in specifically the peak and the valley. So here's the curve. There's what it's doing in those 2 different sections. So calculus, study of change. Well, when we were talking about curves, very often we talked about doing tangent lines. So let's zoom in on the first 2 graphs, make tangent lines. So in red, I'll do the tangent lines. Well, at this point, the tangent line is doing this. At this point, the tangent line is doing this. Those tangent lines have a very specific slope. You should all know exactly what that slope is. There's no excuse not to. You're calculus students, right? The slope of a horizontal line is not undefined, it's 0. And that's for both. That's what they have in common. Now, if you look anywhere else in the curve, if you look right here, its tangent line looks like this. If you look right here, its tangent line looks like that. If you look right here, its tangent line is like this. They're non-zero. That is what these values have in common. So what do they have in common? The slopes are zero at the maxes and the mins. Asterisks, they can also be undefined in special cases, so we'll throw that into the mix as well. But you can just say both slopes, i.e. derivatives, are zero. Note, undefined can be seen rarely as well. We don't really get into that condition too often, but I will throw it into the instructions on how we can do this. All right, so the slope is zero. That's the entire backbone of what we're about to do for finding critical numbers. Actually, let me not say it that way. To find all relative extremum. We'll get to the critical number part in a bit. First, find f prime of x. Why are we finding f prime of x? Because we need to talk about their slopes, and derivatives are slopes. Second, find the critical numbers where the x values f prime of x is either 0 or undefined. If you're dealing with polynomials, the undefined part isn't an issue. If you're dealing with rational functions, then it is. Polynomials can't be undefined. You should know that by now. Rational functions can. So with these rational functions, under rare circumstances, you can get extrema when there's an undefined section. It's not typically seen, but it can happen. Third, remember how in pre-calc 1 we did test points for talking about increasing and decreasing, things like that? Well, we're going to go back to that basis. Use test points to the left and right of each critical number. Maxima occur. I don't want to tab that actually. So this is just an extension of the third step. We're still in the third step here. Maxima occur if f prime of x, if the derivative is positive on the left and negative on the right. The critical number. Vice versa, minima occur if the derivative, I can type, I swear, is negative on the left and the derivative is positive on the right of the critical number. This is called the first derivative test. This is known as the first derivative test. The reason we call it the first derivative test is because we're using the first derivative to test out what happens. There's also a second derivative test, spoilers. Guess what you used for that one? We'll talk about that another day. So the greater than 0 and the less than 0 part, that's just saying positive or negative. So if you wanted to just, abbreviate things if the derivative is positive on the left and negative on the right, or if it's negative on the left or positive on the right. Now that memorization seems very random at first. And guess what your teacher did? Your teacher never memorized it that way. Nope. I love pictures. A picture is worth 1,000 words. Now, if you were going to memorize it that way, if you can get it, that's fine. Let's use pictures to figure this out. So on the left, I'm going to draw an upward facing parabola. And I'm going to have a little point right here, which would be the min. We can tell it's a min because we're looking at it, it's the lowest point. Now let us paint some tangent lines. At this point right here, that slope is negative. This point right here would also be negative. All of these points would be negative. I'm sorry, all of the slopes at these points would be negative. Every tangent line drawn here would all have negative slopes. Let me in fact, without doing the dashes, I much prefer the dashes, but I'm gonna have to do it this way so I can erase. Here's a tangent line right here. Its slope is negative. Let me do another one. Let's get a little closer. Here's the tangent line right here. Guess what? Its slope is negative. If I go extremely close to it, right here, it's going to be practically flat, but that tangent line would still be negative. On the left side of this thing, on the left, all tangent lines are negative to the left. So I'm kind of splitting this thing in half. That's awful. I'm visually splitting this thing in half. I'm thinking about tangent lines on the left. Now this tangent line, that slope might be -1. As I get closer and closer, it's going to go to 0. It might be -1/2, then -1/3, then 0. Maybe it's 5, 4, 3, 2, 1, 0. -5, -4, -3, -2, -1, 0. But on the right, I'll do these tangent lines in blue. Here's a tangent line right here, and that one's positive. It's probably something like 4. And then let me get closer. This one is a little flatter. It's probably like 3, but it's still positive. Let me get closer. This slope is still positive, but it's smaller, so it's probably something like 2. Let me get super close. This one is practically flat, but it's still positive. It's probably like 1 or 1/2 or 1/3. But every single tangent line on the right, all of them have to be positive because it's going down and then it's going up. It's decreasing and then it's increasing. So if it's decreasing, that means the slope is negative. If it's increasing, the slope is positive. Again, if you're decreasing, the slope is negative. If you're increasing, the slope is positive. The first derivative tells us all these things if you look at certain x values. But specifically at 0, that tangent line has a slope of 0. So I like this picture, decreasing, increasing. The slope is negative, slope is positive. That is how I know I've got a local minimum. If it goes down, then comes up. So again, down, up. Your m is negative on the left, and it's positive on the right, which makes that a minimum. Flip the script, draw a downward parabola. So this point has to be a max. You get the same argument. I'm not going to draw the 50 lines this time. Now on the left side, all of your tangent lines are positive slopes. On the right, all of your tangent lines are negative slope, and the closer you get to that point, the more it goes towards 0. And at that point, it is always exactly 0. Oops, why did I draw the downward again? Go. So when you have a max, your slope goes from negative to positive around it. So for the test point stuff, what you do is you find the critical numbers, which are your potential your potential extrema, your potential mins or max. So when you set your derivatives equal to 0 or undefined, which still involves a 0, we'll see one later. When you do that, you're finding it could be a maximum, it could be a minimum, you don't know yet. To find out whether it's a max or min, you're going to plug in x values surrounding the critical numbers and find out whether the derivative is positive or negative. If it goes positive then negative, it means it's going up then down, so it's a max. If it goes negative then positive, it means it goes, I wrote these backwards. I wrote this backwards. Shoot. Right here, this was supposed to be the positive, this was supposed to be the negative. I'm sorry. You're positive on the left, negative on the right. If you're decreasing then increasing, if it's negative then positive, it's a minimum. If it's increasing then decreasing, then it's a maximum. You are not plugging function values, you're not testing function values, you're testing derivative values because you need to be observing the slopes. All right, so paired with this, we can draw graphs of functions by plotting the extrema first and bending to them appropriately, in addition to using the leading coefficient test if needed. So that's a pre-calc technique. You can dust off that. It's based on whether the leading coefficient is positive or negative, and it's also based on the degree of the polynomial, whether the ends both go up, both go down, or a mix and match. I'm not saying you have to do that. Back in pre-calc, we used the leading coefficient test. We found all the zeros, and we would make sketches based on that. So I'm going to erase this in a second, but back in pre-calc, you would say like, all right, the ends go up and up. Oh, well, that was, somebody said something.
Look at the markers when I'm about to bring to your house. I'm about to bring these to your house, Mommy.
Oh, okay. What are markers?
If you could turn your mic off, that would be great. Appreciate it. Thank you very much. And hi to your youngin as well. I hope they're learning some calculus. So back in 161 or pre-calc, you would plot zeros and all your intercepts and stuff, and then you would bend, you would have multiplicities, and you'd say, all right, well, I know I'm going to bounce on this one, and I know I'm going to bounce on this one or cross on this one, and you would make your graphs based off of that idea. But then you'd have these little peaks right here that you couldn't necessarily find the height of. No sweat there. You had these peaks and valleys that you couldn't necessarily find the height of because you didn't know exactly what x value they occurred at. And if you can't find the x value, you can't find the y value without just pulling out a calculator and going, there it is. Calculus, we don't really focus on finding the zeros as much, more so we focus on finding the peaks and valleys, because we tend to relate this to production, and you like producing at maximum outputs or maximum profits. So you want to be at the peaks, or maybe you want to minimize your losses or minimize your expenses. So that was the pre-calc way. In calculus, what we go through and we do, and we find the extrema. So we'd say this was a max and this was a min maybe. And since this is a max, we know we point down from there. Since this is a min, we know we point up from there. And then you just go through and connect the dots. So I don't know why I did that. That was just a sleight of hand. So you do that, you connect there, you make them bend like normal polynomials. It's just a different graphing approach. And I'm not saying we can't find the zeros as well. We certainly could. They might be difficult to find, but the potential is there. So we're going to try graphing some lines in this respect. Example 1. Graph the function by finding critical numbers, identifying the specific extrema, and behavior if needed. And our function f of x is going to be x cubed minus 12x squared minus 60x plus 36. So there's our function. Now I'm not pulling out a graphing calculator for this until the very end. Until the very, very, very end. So this is calculus class. Calculus is derivatives and integrals later. We should probably be doing a derivative. Yeah, that's what I said. We want to find the extrema. To find the extrema, we need to know where the derivative 0 or undefined. Derivative, this is a polynomial, so we're going to just power rule everything. So f prime of x, the derivative of x cubed would be 3x squared. You should be able to rocket through these by now in this chapter. Minus, drop the 2 out front. 2 times 12 is 24. Decrease the exponent by 1, so that's a 24x to the first, which again, I don't like writing the 1. Kind of makes it look like a derivative. Then minus, the derivative of 60x is 60 because that's a special case of the power rule. The derivative of 36 is 0. So there is our derivative. Now this is a polynomial. It can't be undefined. So we only set it equal to 0. You can't set a function equal to undefined. There's another thing that you'll do that we'll talk about later. But just remember that polynomials are defined everywhere. We're going to set this equal to 0 to find our critical numbers. As we said, at all of those peaks and valleys, their tangent lines are always horizontal. So we set the derivative equal to 0. We've done our calculus. The rest is algebra. To set this equal to 0, well, it's got an x squared, so factoring is going to be involved. There is a GCF of 3 that you should take out first to make things easier, to make the factoring easier. So that's x squared minus 8x minus, what's that, 20? So that 0 equals that. Factor pairs of 20 that subtract to 8, well, we got 1 times 20. That's 19, so that doesn't work. 2 times 10, well, that difference is 8, so that's going to be it. 4 times 5 would have a sum of 9. We're supposed to be taking a difference, so that's obviously wrong. So we go 0 equals 3 parentheses, x 2, x 10. 2 times 10 is 20, 10 minus 2 is 8. We got to make sure that comes out to a negative 8, so it's a positive 2 and a negative 10. Your signed arithmetic skills have to be on point. Your factoring needs to be on point. If you can't factor, calculus is going to be difficult. To set each of these equal to 0, we've got 3 equations. We set 3 equal to 0. Then we set x plus 2 equal to 0. Then we set x minus 10 equal to 0. 3 equals 0 is trash. 3 is not 0, so we throw it away. Subtract 2 on both sides and you'll get x equals negative 2 for the second equation. Add 10 to both sides and you'll get x equals positive 10 from the third one. These are our critical numbers, negative 2 and positive 10. These are the locations of our extrema. We don't know if they're maxes or mins yet. They also can be neither. Some critical numbers turn out to be neither a max or a min. The specific condition is we need to see this thing decreasing on the left and increasing on the right to be a min, or increasing on the left and decreasing on the right to be a max. Which again, when I say increasing and decreasing, that means positive and negative derivatives, positive and negative slopes. So now we need to test around these critical numbers in the derivative, not the function. The function doesn't talk about how it's changing. The derivative talks about how it's changing. So here's what I like to do. Come on, give me my other color. Ah, boy. Oh, there it is. Okay. I like to draw a little number line kind of thing. And let's put the critical numbers up there, the negative 2 and the 10, in appropriate spots. So negative 2 would be over here. This was a critical number. And then 10 would be over here. This was a critical number. There are three regions. There's the region to the left of negative 2, there's the region between them, and the region to the right. Let us use numbers to the left, middle, and right of those. So I'm going to use negative 3 as a test point. I'm going to use 0 as a test point, and I'm going to use 11 as a test point. Are those the three values you have to use? Absolutely not. I could have used negative 4 instead of negative 3. I could have used negative 100 instead of negative 3. I could use negative 2.1. As long as your test point is something to the left of negative 2, then you also have one between negative 2 and 10. 0 is the most convenient number. And then one to the right of 10. 11 is pretty convenient. 12 would be good. 15 is okay. 20, you're getting too big at that point. But every student could do different test points and still make an accurate analysis. It's not about the number. It's about being a number in the right region for all three of them. So we are going to plug the negative 3, the 0, and the 11 into f prime of x. All we care about for the outputs is whether they're positive or negative. We only care if the answers are positive or negative. That's all we care about. So I'm going to leave some space up here to come back to. So f prime of negative 3. Now, our derivative was the 3x squared minus the 24x minus 60. You can certainly use this version, but it's easier to use the factored version. It's easiest to use the factored version. EASY. So 3 times negative 3 plus 2 times negative 3 minus 10. I'm plugging it in here. I'm saying that's the easiest version, but it's not 0 equals. It's going back to the original f prime of x. You will get the same answer if you plugged it into 3x squared minus 24x minus 60, but here I don't need to know what the numbers are. I just need to know whether each piece is positive or negative. So f prime of negative 3, 3 is a positive, negative 3 plus 2, that's times a negative, times negative 3 minus 10 is a negative. A positive times a negative is a positive. Because the two negatives cancel. That's all I care about. I don't care that this is 3 times negative 1 times negative 13. which is -3 times -13, which would be positive 39. I don't care that it's positive 39. I only care that it's positive, which means the slope is positive. It's increasing. It's going up. I actually didn't leave enough room here, so I'm just going to redraw it after the fact. So to the left of our critical number, we're increasing. Let's come back to that later. Now let's do the middle one. F prime of 0, that's 3 times 0 plus 2 times 0 minus 10, which is, sorry, not 3, positive. Did not mean to hit that. Please don't crash. And it crashed. How much did we lose? Not much. Good. It's not going to let me undo that, so I just got to erase. Okay, positive. The 0 plus 2 is positive. The 0 minus 10 is positive. Positive times a positive times a positive is a positive, and I'm positive on that positive fact. Can anyone catch my error? I did that intentionally. 0 minus 10 is not positive. It's negative. Positive, positive, negative. So f prime of 0 is not positive. Positive times a negative is a negative. So that can very easily happen. You got to be careful. A lot of people just get in the, oh, positive, positive, the last one's positive. No, be very careful. Watch your signed arithmetic. It makes a big difference. So because the derivative at 0 is negative, that means the slope is negative. It means it's decreasing. Now let's do the 11. We're not plugging in the critical numbers. I'm not plugging in -2 and 10. Guess what the answer is if you plug -2 and 10 in? It's 0. We know that because we found those values by setting the derivative equal to 0. All right, so f prime of 11, this will be 3 times 11 plus 2 times 11 minus 10. 3 is positive, 11 plus 2 is positive, 11 minus 10 is positive, and this, excuse me, the derivative at 11, that one is positive, no mistakes made. So therefore your slope is positive. It's increasing again. This graph goes from decreasing to increasing to decreasing. We did this type of analysis in pre-calc 1, but instead of talking about the slope or talk about how it's increasing or decreasing, we were talking about function values centered around their zeros. That's what we did back in pre-calc 1. It's a similar idea, but we're doing this with derivatives instead of functions, so we're talking about change instead of actual function heights. All right, so let me redraw that line from above. I'm going to skip the colors. We got our -3 as a test point. We got our -2 as a critical number. We got our 0 as a test point. We got our 10 as our critical number. We got our 11 as a test point. So here's what we have got out of this. Until we hit the critical number of -2, we were increasing. Until we hit the -2, we're increasing. What does that look like? It looks like we're doing this. This is what increasing looks like. It doesn't have to be in a curve. You can draw this as a straight line if you want to, but we tend to be dealing with polynomials, so they tend to bend. So until we hit the -2, we are increasing. But then, after the -2 critical number in the region where the 0 is, we saw that that derivative was negative, so it's decreasing. That means from the -2 to the 10, we're going down like this. We're decreasing. And again, it might be a straight line, it might be bending, it might bend quicker, it doesn't matter. But then, to the right of the 10, specifically at the 11, or the 10.5 or the 12 or a million or whatever, we're increasing. So from 10 on, these are like walls, we are increasing. So it's back to going up and bending. These do not have to be drawn, but I think it's another visual flair that helps. So around the -2, here's the point -2, we're increasing and then we're decreasing, so that looks like a max. That's the red and the blue. We're increasing and then decreasing around the -2, which means it has to be a max. Around the 10, if here's the point for the 10, we were going down and then we were going up. Oh, I drew that point just a little too high. It should be here. We're going down and then we're going up. That looks like a min because it's the lowest point. I didn't have to go through all of this specific. It occurs if it's a positive derivative on the left and a negative on the right, or a negative on the left or positive on the right. I used visual cues to help make that analysis because it's clearly if you go up then down, you're going to have a max. If you go down and then up, you're going to have a min. And those critical numbers are supposed to be at those, well, critical points, the max or the min, unless it's just some weird case. Like if you were to increase and then increase, that wouldn't be a max. If you were to decrease and then decrease, that's increase, increase, that's not a max. Decrease, decrease, that's not a min. Increase, decrease, that's a max. Decrease, increase, that's a min. Okay. Now I want to get rid of what I just wrote, just that part, because I'm going to need that space for graphing. So we were supposed to graph the function. We have now identified the specific extrema. We have a local max at -2 and a local min at +10. So we have a local or relative max located at x equals -2. And we have a relative min. I don't know why I squished it together so much that time. Located at x equals 10. We don't know the heights though. What are the heights? We need f of x. The function tells us the actual heights. So if we go back to the original function, x cubed minus 12x squared minus 60x plus 36, let's just pull out a graphing calculator for the sake of time. Hello? I was kind of hoping that that was going to fix itself eventually. Hopefully this works. So we got -2 cubed. That looks okay, I guess. Minus 12 times -2 squared minus 60 times -2 plus 36. Let me make sure I've got everything typed correctly. -2 cubed minus 12 times -2 squared minus 60 times -2. That looks good. We hit enter and we get 100. So f of -2 is 100. You do need to know the actual locations of those points, not just where they're located at, but what they are. Then next, let's do f of 10. So f of -2, that was our max. So this should be the maximum value. We'll label that in a minute. Now let's do the 10. Let's go back to our calculator. Let's do 10 cubed minus 12 times 10 squared minus 6 times 10 plus 36. That looks good, doesn't it? 10 cubed minus 12 times 10 squared minus 6 times 10 and the plus 36. I think I have a typo on my notes. I have a wrong number there. I just want to make sure this is right. Yeah, that's right. Okay. I just need to scratch out that number on my notes. No big deal. Okay. So f of 10 is negative 224. Now you might think that, oh, okay, well, if this was supposed to be the minimum for some reason, let's say this was supposed to be the min and this was supposed to be the max, you might think, well, that makes no sense. Why would the max have a smaller number than the min? Because local extrema are only talking about right around them. You can have maxima that are smaller than minimum when you're talking about local extrema. Anyways, the 100 and the 224 are the actual outputs. So the relative max is 100, and the relative min is negative 224. So there's no disassociation for this one, but it could have happened. That's something to be careful with. You don't want to overthink it. All right, so now that we know where these peaks and valleys are, let's draw them that way. Let me zoom out just to give myself a little more space to make a good graph. There we go. So our x values aren't varying too much. We got a negative 2 and a 10, but the y values are definitely varying wildly between 100 and negative 224. So let me put let's just say the 100 is here, and let's say our negative, no, I need to make that a little lower for scale. Let's say the 100 was here, and the negative 224 was here. Then let's say the x equals negative 2 is right here, and the x equals 10 is over here. I just don't want to have 50 million hash marks. I gotta sneeze. I'm gonna try and mute this in time. All right, I got it. All right, so negative 2 comma 100, that's left to 100. There is the relative max. And I'm actually going to write the word max by it as a helpful reminder, as a very helpful reminder. Then the other point was the 10 comma negative 224, so that's over here, right? 10 down 224. And I'm going to write min by it as a helpful reminder. So now imagine that you had your nose to these 2 points. So this little green box, which I will erase in a minute, this is where your nose is and all you can see. If that's a maximum, that means around that point, it has to look like this. It has to be going down of both sides around it. It has to go from increasing and decreasing. There's nothing else that curve could do in that region. So what you do is you just draw a little segment right around it, demonstrating that. Because that has to be a max, it has to look like that in that region. And I've kind of done that a little ugly, but I'll make it better. That's what it has to look like in that region. It might be tighter, it might be wider, but it has to look something like that for it to be a local max. There's nothing else it could be. On the contrary, the minimum, again, if you nose to the board just around this point, because it's a minimum, it has to be going up everywhere around it. So what we do is we draw going up on both sides. And again, the wideness or narrowness of yours will just be based on how you want to make it. Now again, back in pre-calc, we would know some zeros. We could set the function equal to 0, And you still could arguably do that here, but trust me, the numbers are not pretty. They're not going to be whole numbers, at least not all of them. I can guarantee that. But we don't need it. We don't necessarily need to know the zeros in calculus. We tend to be much more interested in the extrema, the maxes and the mins, the best and or worst. Well, these are the only extrema. So what that says is there's no other time where it's not like if there's a point here, there's no way it could be going up on both ends. If there was a point here, there's no way it could be going down on both ends because we have found all of the locations that can happen. So all we do is just try and connect everything and keep moving in the directions that you see. So we're going down from this max, you're going up from that min, so it's probably going to look something like this. That's not the best. Something like this. That's not the best. Not so much a line. I want to flatten out this a little. Let me just flatten that out. That's about what it should look like between those two. The steepness of this, sketching this by hand, how steep that is, I'm not worried about that. What I'm worried about is that it doesn't look like this. You don't have extra hills and valleys. And it doesn't even have to be a ridiculous amount. It just can't look like that because then you've got an extra hill and a valley, which they don't exist. We found all of the ones. So it's got to look something like that between them. To the left of the max, it's going down. You can't do this because that would imply another extrema. You can't bend or turn around at any point. You just got to keep going down, 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 forever and ever. And to the right of the minimum, you can't turn back around at any point. You can't do this because then you've got an extra extrema. So you just keep going in that direction. Up, 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 up. And there's our sketch. That's the most detail I would need to see if this was paper pencil. I don't need to know the locations of this, and this zero. I don't need to know those locations necessarily for what we do in calculus. I'm not saying they're not important values. I'm not saying that maybe your boss wouldn't need them for some reason. I'm just saying that in here, it tends to be less important. We're just finding a new way to graph things. Again, what's important is that you don't have extra zigzags in other regions, other peaks and valleys that don't exist. You're finding the maximum number of peaks. And if you remember back in pre-calc, we talked about the maximum number of turning points. It was always one less than the degree. This polynomial was of a degree 3. There are 2 turning points. Turning points are extrema. Kind of just a little reminder. What's happening? Turning points are the extrema. So there's 2 turning points in this graph, which is 1 less than the degree. So that's good. If I drew this and there were 4 turning points or even 3 turning points, we've got too many. It would not be correct. So that is how we go about graphing polynomials in a calculus concept. Another thing that we can check is the leading coefficient test, LCT leading coefficient test. This function was approximately, where's my squiggle? There we go. Just looking at the leading term, which governs the growth at the ends, was x cubed. X cubed, that little caret just means x cubed, which x cubed graphs go down on the left and up on the right with a positive. And that's exactly what happened here. It went down on the left and up on the right. So this was using the first derivative test to find our extrema and ultimately make a sketch of a graph. Again, if this function had zeros, they were easy to find by factoring, you could do it. This is not easy to factor, I can guarantee that. You would definitely need to list all the possible rational zeros, which are the factors of 36, do synthetic division to see which one makes the function 0, and I'm not even going to guarantee that any of them do. Let's pull out a calculator and just see. I'm kind of curious if this will work. Let's see what this looks like. X to the third minus 12x squared minus 60x plus 36. This will be the last thing we do. It looks like just the outline of my TI-83 is missing. And we can hardly see anything because this function is dealing with pretty large numbers, so we should probably zoom out, or at least make the heights different. I'm going to leave the x scale the same, except I'm going to go to 11. The y scale, let's make the y minimum negative 500, and the y maximum, let's make that 200. And that did not go down enough. So window, maybe I had a typo somewhere. You know what, my 764 was right. Why did I get a different number earlier? That's all I got to change. I knew that 764 is right. What did I do wrong earlier? Negative 10 or 10 cubed. Oh, I know what I did wrong. I had a double negative situation right here that I didn't account for. No, I didn't. That's not right. Did I do 60? I did 6. Look at that. That's a 6, not a 60. It was negative 764. Okay, so let me just correct that in my notes real quick, that this should be negative 764. As should this. As should this. Sorry about that tiny little arithmetic error, but the point is still here. Look at the graph that we sketched out and look at the graph that we got. As I said, the steepness here, now because I was scaling this to be about 2.5 times that distance, this should be a lot further. I want to redraw that graph to emphasize that. I'm so sorry. So here's my -2, here's my 100, here's my negative 764, and here's my 10. So we had this point and this point. Then we do our basic, oh, they were maxes and mins. Then we connect them. Then we continue the trends on the outsides. Now that looks a little better to the graph. And again, that's just because I had my graph scaled poorly because I had a wrong value because I missed a 0 when I typed my calculator. I know I typed 60. What happened was this thing, if I click too quick, it doesn't register. So that was my bad. I'm sorry. I'm going to keep apologizing. Sorry. And I'm not much of one to apologize. So that graph looks pretty good for a sketch, considering we didn't use technology at all to make that, besides finding our error. Trace. If you type in -2, you can now see that. If you type in +10, you can see that. Now the point of this was trying to find the zeros, trying to find the locations here. This looks like -1, 2, 3, -4. If I type -4, what do I get? 20. It's close, but it's not 0. And if I try and hone in on that, it's going to be some ridiculous value. You might think 0 works. And that's 36. It's not quite there. You might think it's 0.1. 0.1. See, there it was. I clicked something and it didn't register. 29. Not quite. I mean, you can't find these zeros analytically, even with the techniques we taught you in pre-calc. But again, I didn't want the zeros. I didn't ask for that. They're generally not as interesting at a calculus level because we have, in my opinion, a better way of graphing, because in calculus, we tend to be more interested in the peaks and valleys. So I'm going to go ahead and
All right, so we're going to take our break. We'll be back at 8:03, and we'll pick up exactly where we left off.
left off in 3.1. So I'm just going to really quickly pass over what we've done, which was the first derivative test. That's the short way of saying what all this says. It's the first derivative test. The first derivative test says that we can find the peaks and valleys, the local extrema, the local max and local min, whatever you want to give these things names of. Peaks, valleys, local max, local min, your local extrema. By taking a first derivative and setting it equal to 0 or wherever it's undefined. Specifically, the undefined part deals with rational functions, which is in 3.3, which I just said that we will hold off on until the end of the semester if we have extra time to go over and cover. For us, it's much more important to discuss the behavior of polynomials than rational functions. And I'm not saying that rational functions have no importance. I'm just saying these are more important, and it's an issue of time now. All right. So in your polynomials can have all sorts of bumps. They can have all sorts of hills and all sorts of valleys. You could have 5 or 4 of these things, or 9, or just 1 of each, or maybe just 1 of one and none of the other. And you can discover this by using the first derivative test, which says take the derivative of the function, find what we call the critical numbers, which is where the derivative is 0 or undefined. So right now we're really just focusing on the 0 aspect. And then you'll use that test point method, which you should be kind of familiar with from pre-calculus. But instead of doing test points in the regular function, you're doing test points in the derivative because you're trying to see when this thing is going up or when it's going down. And we said that a maximum occurs if the derivative is positive to the left and negative to the right. And I'm going to draw these just really quickly and erase the stuff that you can see. So a derivative being positive and then negative means, all right, here's its positive, here's its positive. And then after this point, all of a sudden it goes negative, 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 negative. So again, that's a derivative that's positive and then negative, and it's 0 right here. It is 0 at the peak, and that would be a max. Or if the derivative, this is the second sentence, a minima occur, or a minimum occurs if the derivative is negative, which means it's going down to the left of that point, then here's our critical number. And then the derivative is positive, so it's increasing to the right. Decreasing, increasing. This one on the left is increasing, decreasing. You have to remember that concept. All right. Oops. Too far. All right, so that's our first derivative test. And again, the test points, so let's just say that we had a critical number of 5. We'd want to use test points of something like 4 and 6. Find out what happens to the left and the right in the first derivative. We call it the first derivative test because we need to find the first derivative and plug the test points into the first derivative. And then we did an example right here. So we found our critical numbers to be -2 and 10. We did test points to the left, center, and right of those values. We plug those test points into the derivative, not the original function. And I mentioned that it's easiest to plug it into the factored version because then we don't really care what the numbers are, just whether they're positives or negatives and their products and quotients. And then you can use your sign rules for multiplying and dividing numbers. Positive, negative, positive. So it went increasing, decreasing, increasing. So it went increasing, then the critical number, decreasing, then critical number, and then increasing. And I didn't make this part bend to make it look super appropriate there, but that's not the point. It's just, and I even mentioned that you can do these with straight lines. You could say it's increasing here, then it's decreasing here, and then it's increasing here. That looks like a peak. That looks like a valley. The same concept can be demonstrated with straight lines instead of curves. But again, I don't want to jumble my notes up. So with that being said, let's get into, oh yeah, and we had my famous typo, which my notes had the number right originally, and then I typed something in my calculator wrong. Slightly annoying. So let's get into another example. Where did I put my piece of paper? Oops. There we go. Example 2. This to be in black. And we're going to graph by finding all local extrema. And this will be f of x is equal to Let's go to a simpler one, x squared plus 2x plus 2. And I'd like to point out, someone sent me an email about homework questions being a little different, maybe a lot different than the homework. My opinion is a little, they may have said a lot, it doesn't matter. I don't do every single aspect of what you'll see in the homework in our notes. That's how college math classes work. We're supposed to learn the basics and then try and expand upon things just a little bit. And you will see that in 3.1's homework, you'll see that in 3.2's homework, and you'll see that pretty continual moving forward. But as you notice, my test questions are much more similar to the notes. And in the homework, you still find questions that are similar to the notes, but you'll get some more conceptual questions like, here's the graph of the derivative. What do you think you can say about the regular function? So things like that, or maybe just some A, B, C, D questions that are conceptual. And again, you've got infinite many chances on a question. So there's no reason to not ultimately get that right. Okay, but back to this point. So here's our function, graph by finding all local extrema. We're going to use the first derivative test, which means we need to find the first derivative. Power rule, bring the 2 out front, decrease the exponent by 1, plus the derivative of 2x is just a 2. I'm going to be going lightning fast through simple derivatives like that now that everyone got A's, B's, and C's on the first test. That was excellent. So there's our first derivative. And then we set this equal to 0 or undefined as necessary. Again, that's for rational functions. Specifically, to set something undefined, that means you're setting the bottom equal to 0. So if you wanted to try any of that, just paper pencil if you look through your textbook. Your rational functions have tops and bottoms. It just means you set the top and the bottom equal to 0 separately. That's what it means by setting it equal to undefined. All right, so we go 0 equals 2x plus 2. Not a lot of crazy intense algebra to have to solve here. Subtract 2 on both sides. I don't even know why I feel the need to show that work. That's negative 2 equals 2x. And then we're going to divide both sides by the 2. And we will get negative 1 is equal to x. And that's our critical number. Remember, we call critical numbers the values we get from setting the first derivative equal to 0, or where it's undefined, which is when its bottom is 0. Once we have this, and it's only one critical number, the last example had 2. You can have 1 or 5 or 19 critical numbers. It just makes the test points, a little more involved if you've got 19 of them instead of 1 or 2. And generally, it's just 1 or 2 or 3. So let's, over here, set up our number line. And let's just have the negative 1 be in the center. This will be our critical number. And then let's do our test points to the left and right of that. So a number to the left of negative 1. Well, negative 2 is the smallest whole number to the left of that, so that's what I'll use. And then a number to the right of negative 1. I like 0 whenever I can use it, and 0 is to the right of negative 1. These are not the only 2 test points that could work. I could use negative 3 and a million. I could use negative 5.2 and 1.7. You shouldn't use decimals, in my opinion, if you don't have to, but you could. So we're going to plug these into the first derivative. So we're going to find f prime of negative 2. Now, I didn't write the factored version of this because it's linear. There's really no need to do that. If you need to, you can, but you're just going to get 2 times negative 2 plus 2. Which is negative 4 plus 2, which is negative 2. See, this is a little different than how I did it in the previous example. The previous example, I only worried about the signs because it was factored or written as a fraction. This is not factored, so you do actually need to carry out the math. So if f prime, I didn't give myself enough room there. I just need a little room under the number line part. Negative 2. That was 2 times negative 2 plus 2, which is negative 4 plus 2, negative 2. So that says it is decreasing. The derivative is decreasing. It's going down in that section until you hit the critical number. So from anywhere to the left of the negative 2 up until you hit the negative 1, we are decreasing. And you could draw this with a straight line. I went just a little far. Come on. You could draw that with a straight line, like so, or you could draw it bendy, and I prefer to draw it bendy. So this is decreasing, 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 up until we hit that critical number. Then we're going to do f prime of 0, which is 2 times 0 plus 2, which is 0 plus 2, and that's positive 2. Therefore, it is increasing. So in that section, it's going up as we move right. Now, again, the critical number is the barrier where we change from decreasing to increasing or vice versa, or whatever might happen. So to the right of the -1, we're increasing. You don't have to draw it continued from there. You can draw it however you like. Just do this. So we're decreasing and then increasing. And if you just drew those two shapes together, decreasing and then increasing, or if you draw it with the straight lines, and I don't want to draw it next to that part. So again, here's your -1. That means we're going decreasing, and then we're going increasing. So the -1 has to be a relative min, because we went down then up. If we went increasing then decreasing, that means the critical number would have to be a relative max. That's not what happened though, so I'm going to erase it. It is a very easy series of pictures to draw to find out whether it's a max or min. You had that very detailed written out, oh, if it's positive on the left and negative on the right, then it's a maximum. And that works, but I just think that the pictures are worth 1,000 words. So I always draw those little pictures each time. All right, so we know there's a relative min at -1, but we also need to know what is the height, what is the output, what is the min. What is this min? This relative minimum. So we actually have to go to the regular function, find the height at, that's a -1, isn't it? Yes, it is. So f of -1. Well, that function was x squared plus 2x plus 2. So we're doing -1 squared plus 2 times -1 plus 2, which is +1 minus 2 plus 2. The negative and the positive 2's cancel, so the output's 1. So that f of -1 is +1. In other words, we have the point -1 comma 1. And that point should be a relative min. So that is probably enough to draw our picture. So let's go ahead and set up our graph, set up our axes, make sure you label them. X, Y. We have the point -1 comma 1. Let me make sure I get my signs in the correct order. -1 comma 1. So there's our point, and that's the critical number. If you need to write somewhere that it's critical number, you could write it really teeny, CN if you wanted to. I'm not going to, but you could. Now, around that point, we were supposed to be decreasing, then increasing, decreasing, then increasing. So in the neighborhood of that point, it's supposed to look something like this, basically, going down and then going up. Now, there are no other extrema. Remember, in the first example, we had maybe a relative max here, and then it made it bend to that like that, turn around, and then keep going. That's not what's happening here. This is the only critical number, meaning there's not going to be anything else pulling it back around. There's nothing to say, oh, here's a max and then turn back around. You just keep on trucking. You just keep going up and up and up and up on both ends. So we're decreasing until we hit the -1. We're increasing after that. There's our graph. Now, maybe this graph is a little tighter. Maybe it's a little wider. There are lots of different ways you could determine that. You could just find extra function values. You could find f of 0, f of 1. To get a slightly more accurate quadratic, which is actually what we prefer you doing back in pre-calc 1, but in this class, since I only said to graph it based on the extrema, that's it. That's all I need. This is a very atypical example. This one's kind of simple. This is a little too simple for a test, in my opinion. The test problems are going to be more the nature of the previous one, and because of that, we'll do one more like it. All right, example 3. Same instructions, graph by finding extrema. And our function this time is going to be x cubed plus 3x squared minus 9x minus 11. So find the first derivative. F prime of x would be 3x squared. Bring the 3 down, decrease the exponent, plus. Bring the 2 down. There's a 3 in front of it, so you multiply. 2 times 3 is 6. Decrease the exponent by 1. Minus. The derivative of a linear term is just the coefficient. And then for the negative 11, the derivative of a constant is 0. So this is our derivative. Now we take this and we set it equal to 0. So we go 0 equals 3x squared plus 6x minus 9. We're not worried about where this is undefined. It's a polynomial. Polynomials are never undefined. If this was a fraction, then we'd be setting the top and bottom equal to 0. Setting the bottom equal to 0 being the undefined values. And then because there's an x squared, we need to factor this as much as possible. You have got to be on your factoring game. No excuses in calculus to not be able to factor. I know I've said that a million times, and I'll keep saying it. So we got a GCF of 3, so we're going to pop that out. Dividing each term by 3 would give us x squared plus 2x minus 3. Then inside, we can factor that even more. The pair of numbers that multiplies is negative 3, but subtracts to 2 would be 1 and 3. So we go 0 equals 3 times x1, x3. And then we know they're going to have to be opposites to multiply by a negative, and we know that the larger numbers are going to have to be positive to subtract to a positive. So that means it's a positive 3 and a negative 1. If you get this wrong, the rest of the problem is going to be awful. You're going to have very, very bad information after this point. If you can even just swap these signs, if you say x plus 3 and x minus 1, when you start doing your first derivative test, when you start doing your test values, usually what you'll see, usually, not every time, usually, I'm saying usually around these critical numbers, it goes from decreasing to increasing or increasing to decreasing. Once again, that doesn't have to happen, but it usually does. If you factor wrong, that means your critical numbers are wrong, and you probably won't see that increasing to decreasing thing. It'll probably go increasing, increasing, or decreasing, decreasing, which is probably not what it's supposed to do if it's a polynomial. All right, so we got our critical numbers right. Now we set each of these things equal to 0. So we go 3 equals 0, x minus 1 equals 0, and x plus 3 equals 0. The second and the third are easy to solve. Add 1, subtract 3. I'm not going to show the work this time. You get x equals 1 and x equals negative 3. 3 equals 0. There's no x in there. That is hot trash. You throw it in the garbage. You throw it in the garbage. I don't want to have that stuck on my notes, but that's what happens. 3 equals 0 is a lie. 3 is not 0. So the positive 1 and the negative 3, these are our critical numbers. The positive 1 and the negative 3. So we will make our little number line with those up there. We need a negative 3 on the left and a positive 1 on the right. Make sure they're in the appropriate spots relative to each other. Then we'll make our test points to the left, middle, and right of them. A good number to the left of negative 3 is negative 4. That's our first test point. A good number between 1 and negative 3 would be 0. I always use 0 if I can because it's an easy number to plug in. And a good number to the right of 1 would be 2. Once again, literally millions of options for these test points. They are not the ones you have to use. I'm going to leave myself a little space here so I can show that like decreasing, increasing, decreasing thing, or whatever pattern it has. So now we're going to plug in the test points into the first derivative. So we're finding f prime of negative 4. Now you can use the 3x squared plus 6x minus 9, and you'll have to actually put up with the numbers the whole time. Or you can use the factored version, this 3 times x minus 1 times x plus 3, and get the job done more efficiently, in my opinion. So this is 3 times negative 4 minus 1 times negative 4 plus 3. 3 is positive. Negative 4 minus 1 is negative. Negative 4 plus 3 is also negative. And a positive times a negative is a positive. So it's increasing. Once again, I didn't really leave myself enough room. I can fix this though. Let me just erase this 2. Put it a little higher. Let me erase the 1. That just a tick higher. Go. That'll be good enough. So that says it is increasing. We're talking about the derivative, so it's increasing there. Now, that says until we hit the -3, we're increasing. We're going up, whether you draw this as a straight line or a bendy line, a bendy curve. I said that intentionally wrong. So this would represent increasing. Now let's do in the middle, the 0, f prime of 0. What's 3 times 0 minus 1 times 0 plus 3, which is a positive times a negative times a positive. 3 is positive, 0 minus 1 is negative, 0 plus 3 is positive, and that is a negative. So therefore, it is decreasing in the range of the 0 between those two critical numbers, whether you draw it as a straight line or if you draw it as a curve to represent that you're decreasing. Like I said, you don't have to show them connecting all smoothly like the graph is probably going to do. You can have it kind of disassociated like this. And then finally, the derivative at 2. So that's 3 times 2 minus 1 times 2 plus 3, which is positive, 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 therefore increasing. So we're back to either, again, from 1 on, straight line pointing up, or a bendy curve pointing up. So if here is your -3, we're increasing to the right, to the left of it, excuse me. We're increasing to the left of it, increasing to the left of it, and then we're decreasing after that. So that means in that region, that has to be a max. If this is the point that's your 1, to the left of the 1, not over here, just immediately to the left of the 1, we were going down, we were decreasing. So we're decreasing until we hit the 1, and then after the 1, we're going up, we're increasing. So we're going up, meaning this has to be a relative min. Again, I didn't have to memorize the whole decreasing, increasing aspect. I just drew the picture. I said, okay, we're going up to the left, we're going down to the right. Clearly, that's a max. We're going down to the left, up to the right. Clearly, that is a min. I am telling you that picture makes things so much easier than memorizing just plain Jane text. Oh, if it's increasing to the left and decreasing to the right, it's a max. The picture says it better. Well, now that we know what type of extrema they are, we still need to know their function values. So now we need to go back to the original function, the x cubed plus 3x squared minus 9x minus 11, and actually find the outputs. So let's find f of the -3. So that is -3 cubed plus 3 times -3 squared minus 9 times -3 minus 11. Let me make sure I have all that right since the function's not on the screen. Yes, okay, that's good. The -3 cubed is -27. Watch your signs with arithmetic like this. The -3 squared is +9, but then times that other 3 is a +27. This -9 times -3 is a other +27. And then the minus 11. The first 27 positive and negative will cancel. 27 minus 11 is 16. So f of -3 is equal to 16. So the point is -3 comma 16. That is our relative max. When we do our f of +1, that's 1 cubed plus 3 times 1 squared minus 9 times 1 minus 11, which is 1 plus 3 minus 9 minus 11. 1 plus 3 is 4, 4 minus 9 is -5, minus 11 is -16. So the function value, f of 1, is -16. So our point is 1 comma -16, and that's our relative min. Now again, relative extrema are relative only in that very, very small area. These outputs could have actually been swapped. This first point could be -3 comma -16, and it could be a relative min. And this could be 1 comma +16, and it could be a relative max. And you might think, how's that possible? How could the -16 be a max and the +16 be a min? Again, we're only talking locally. Remember, you're putting your nose to that point and you can only see just barely around it. So no, a relative maximum does not have to be higher than a relative minimum. It is for this problem, but it doesn't have to be that way. Again, I'm just really quickly spitballing. You could have a relative maximum that's down here. Here's a relative max. Here's a relative min. This relative min has got a much larger value, maybe positive 16, than this relative max that's maybe negative 16. Again, this is just saying in general, this is not the graph of the picture we're about to make. All right, so we got our 2 points. We know what type of extrema they are. That should be good enough to get the job done. So our heights need to go pretty high, up to 16 and negative 16. Let's just go in even numbers, 2, 4, 6, 8, 10, 12, 14, 16. 2, 4, 6, 8, 10, 12, 14, 16. The x values, we got 1 and negative 3, so we don't really need to go very far out on that. 1, and then 1, 2, negative 3. So we got negative 3, 16. That's left 3, up 16. There's our relative max. We got 1 comma negative 16. Let me just put that on the other side so it's not in the way. That point would be there. And remember, you are more than welcome to put as a little reminder, relative max, relative min with these things, if you think that would help you get this picture. So remember, the relative extreme will tell you what it looks like in that region. So if it's relative max, it has to be going down on both sides of that relative to it. Again, I'm not saying it's decreasing on both sides. I'm just saying both sides point down, which makes it increase to the left and decrease to the right. Then over here at the relative min, both ends have to be pointing up around it because it's going to go decrease, then increase. That is all you need to paint this picture. You just then, because there's no more extrema, that was weird, because there's no more extrema, you don't have to worry about bending. I don't have to worry about bending over here or anything like that. You just keep approaching the same direction. So clearly I need to connect the relative max to the relative min. So we do so as best as we can to make that kind of look like a polynomial. If you wanted to erase the original bends if they're too wide or too narrow, you can. You don't have to use that. I could have started from scratch. And then to the left and the right of it, just keep trucking in the same directions they're pointing. So keep going down, 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 down. And to the right of that relative min, just keep going up, 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 up. And that's all I need in a calculus class. Yes, it is possible for some functions to then find these zeros analytically. But quite often when we're dealing with a calculus style function, they're built so that the derivatives are easy to find the zeros, which tends to make the original function complicated to find its zeros. It's very hard to make a function easy to find rational zeros for the function and its derivative. Usually you only get one or the other. And that's why we tend not to focus on finding exactly what these x-intercepts are. You could certainly confirm them with a calculator after the fact that you've done this, but this is something you're supposed to be able to do by hand. I did not use a calculator at all for this. If I did, I would have a much more accurate depiction of the graph. And when you're working on your homework, I would suggest doing that. Pull out a calculator. If I haven't mentioned, I know I have mentioned this, it just may have been a while, you can download a TI-83 for free. Just Google TI-83 app. That's what I use sometimes in class. In fact, there it is, virtual TI-83. Let's see if this agrees with what we have. Y equals, and this was x cubed plus 3 x squared minus 9x minus 11. Graph. That looks pretty good. You can't see exactly where these peaks and valleys are because we're zoomed in a little too much. So you can change your window, you can change your zoom, you can just go down to zoom out. I know these peaks are 16 and negative 16, so let me just change the y minimum to negative 20 and the y maximum to positive 20. there we go. That is a dang good sketch, just based on 2 points. Now, there are other things you can use to confirm this. You can use the end behavior, as I mentioned, because the leading term here is an x cubed. It's a positive x cubed. That says the left end should go down and the right end should go up. That's exactly what happened. You can also talk about the maximum number of turning points. That was something we had in pre-calc 1, where if you have a third degree polynomial, you can only have 2 turning points. The turning point is always 1 less at most. It doesn't guarantee it, but it says it's a maximum number of turning points. What are turning points? They're the extrema. The relative max is a turning point, the relative min is a turning point. There's 2 of them, so we don't have too many. If I had ended up drawing something like this, that would have 1, 2, 3 turning points, and that's too many because of the x cubed. If it was an x to the 4th, we could have 3. Oops. There we go. All right, so 10:30. What time did I start? About, I think I started at 9:50. This thing would tell me how long I've been recording. I guess not. Okay, doesn't matter. That's 3.1. Are there some more things that we could go into in that section? Sure. Again, like I said, the main thing being dealing with the rational functions. But what I think is kind of weird is they try and have you graph rational functions this way in 3.1, but they don't actually have an official section on it until 3.3. Textbook is not set up that well, in my opinion, because of that. So in the homework, I actually deleted all of those in case we do come back to 3.3. But again, it's not really something you're going to have to worry for now. It wouldn't be on the test. It won't be in the homework. If it is, it was an accident. I was pretty sure I deleted them all. I double checked. So with that being said, let's start our discussion on 3.2. Open up a new file. Hopefully this thing doesn't crash. In fact, let me close the 3.1 document. Maybe that'll help. And this will be 3.2. So 3.1 was the first derivative test. 3.2 is the second derivative test. Using second derivatives to classify maximum and minimum values, and then sketching graphs. So the first derivative test is called the first derivative test because you use the first derivative and test points to find your relative extrema. The second derivative test is called the second derivative test because you use the second derivative and test points to find your local extrema. Do you see how the names tell you everything about it? Well, we need to know exactly why and how we can use second derivatives to find maxes and mins. After you've actually done the first derivative test, I feel, and practiced it, I feel like most people are able to really make sense of it. It makes sense because increasing, decreasing, you're going up and then down. That makes you have a little peak. It's a relative max. So it makes sense to look at the first derivative, to look at how the slope is changing, because we're getting used to seeing slopes go from positive to 0 to negative, or from negative to 0 to positive. But believe it or not, you can actually talk about the change of the change. Remember, that's what second derivative means. First derivative is the change of the function. The second derivative is the change of the change. And it's a little more convoluted sounding to wrap your head around, but we can use second derivatives to get this same job done. So that's what we're going to talk about. And to introduce the concept, we talk about what's known as concavity. Let's see. Concavity, I don't need a colon, shows how a function's graph curls or bends. Functions can be concave up, concave down, zero concavity. It's kind of funny that we have the word concavity in calculus, because in the dentistry world, calculus deals with the gunk between your teeth, and the word cavity, with cavity. I don't know. I just think it's kind of funny how these people chose their words. I'm not much of a linguist expert, and I said that funny intentionally. So I know how some roots of words relate, but I don't know them all. I don't know exactly how concavity meant to be related to math and dentistry, but it's there. Either way. So functions, just like your derivatives, your slopes can be positive, negative, or zero, your concavity can be positive, negative, or zero. So concavity has everything to do with the second derivative. Similar to how slope has everything to do with the first derivative. So when our slope was positive, our derivative was positive. When our slope was negative, the derivative was negative. When our slope was zero, the derivative was zero. Remember, that related to the tangent lines at each individual point along curves. So if your second derivative is positive, it's concave up. If your second derivative is negative, it's concave down. And if it's zero, then it has a zero concavity and can be a special point. All right, so in particular, when a function has zero concavity, it can be known as an inflection point. This occurs switching from concave up to concave down, or vice versa. So if you have the second derivative, sorry, let me not get too specific. If it goes concave up, zero, and then concave up, that's not an inflection point. If it goes concave down, then zero, then concave down, that's not an inflection point. It has to switch. Kind of like to get a relative max, you have to switch from increasing to decreasing. To get a relative min, you have to switch from decreasing to increasing. It's all about changing from one thing to another. So concavity, inflection points kind of feel like relative extrema, but dealing with a second derivative instead of a first. In particular, concave up looks like an upward facing parabola. Concave down looks like a downward facing parabola. In the regions, again, in those little regions, it doesn't say the function's concave up everywhere. We're only talking about a local region. It could be everywhere, but we're only talking about in local regions. So when you're concave up, that means in that region, it looks like this. When you're concave down, it means in that region, it looks like this. And I will draw a demonstration of an inflection point in a few minutes, don't worry. So concave up means we're bending up. This is bending up. Concave down means we're bending down. So you have these U-like shapes, and they're either facing up or down. If it's facing up, facing down, concave down. So I'm going to draw something, and I'm going to erase it after the fact. Let me draw a whole bunch of tangent lines to show you the relationship between the first and second derivative. So here is a tangent line, here's 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 a tangent line. As you're moving along this, these slopes of these tangent lines is getting bigger and bigger and bigger. This number right here might be -4. This might be -3. This might be -1. This is 0. Then +1, +3, +10, +1,000,000 as you keep going and going and going. So when your derivative is getting bigger and bigger and bigger, that's what leads to being concave up. It's not saying the derivative is positive because over here it's negative. It's negative, it's negative, then it's 0, then positive, positive, positive. All we're saying is that the derivative is constantly increasing. F prime is increasing. Wherever you're concave up, your derivative is increasing. Wherever you're concave down, flip the script. We start out with a positive slope, maybe positive 3, then maybe positive 2, positive 1, 0, negative 1, negative 2, negative 3. Your m is getting smaller. Again, we went from like positive 3, positive 2, positive 1, 0, negative 1, negative 2, negative 3. That says that your derivative is decreasing. All right. So I said something earlier about the second derivatives being positive, 0, or negative. Let's actually put that into words on the screen for you to copy down for good notes. If f double prime of x, that's a second derivative. Let me zoom in just so you can make sure you can see that there's 2 of those. That is a second derivative. There's 2 of those little marks. If your second derivative is positive, that says it's concave up. If your second, see, here's the first derivative, here's the second derivative. If your second derivative is negative, then it's concave down. I want to capitalize the U and the D just because, no reason really, just makes it look better. And if your second derivative is exactly 0 at a point, and switches concavity, it's concave up on the left and down on the right or vice versa, and it's an inflection point. So let's draw what an inflection point can look like. We have to switch concavities. We have to go from like an upward facing parabola to a downward facing parabola. So here is me drawing something that's concave up, and I'm going to stop right here, and then I'm going to draw something that's concave down. Now, you would normally have this be the same color, but I just really want to be emphatic with this. And then I'm going to switch this to concave down. Now, let's just say that it keeps going on each of the ends. It doesn't have to. Let's just say that pattern continues. Again, it wouldn't have to. So this point right here, so again, the blue represents concave up because if you just look at the blue, if you don't look at the red, that's an upward facing parabola. So that's concave up. If you only look at the red, that's concave down. You got that downward facing U. But at some point, it's changing. So right there, we're switching from concave up, cup, to concave down. So that point where it switches from one to the other, that is our inflection point. Up to C down, or vice versa, if it had gone from concave down to concave up. If we'd gone concave down, then at some point, we switch to concave up. There's a point somewhere in between these regions, which you can analytically find by finding the second derivative. This would be your inflection point. I'm just going to write IP this time for inflection point. To the left, it's concave down. To the right, it's concave up. So The title of this was Using the Second Derivatives to Classify Maximum and Minimums. All we've talked about really in detail is concavity here. And I'm not even going to do, yes, I will. I want to save the second derivative test since I only have, in my opinion, like 6 or 7 minutes left to talk. Since I said I'd keep it at an hour. Sorry. Okay, so let's find an inflection point. Let's do one example. Find any points of inflection, aka inflection points. I'm actually stealing this from the textbook. This is example 3A. I'm missing a page of my notes. And I don't want to spend 5 minutes digging it out. I think it's just in the folder somewhere. It must have gotten deorganized. We're going to go x cubed plus 3x squared minus 9x minus 13. Really, really similar to one of the ones we did last section. But we're finding the inflection points, not the critical numbers, not the extrema, just the inflection points, which means we need to find f double prime of x. So f prime of x, the first derivative, that would be 3x squared plus 6x minus 9. Now, if we were finding extrema in the last section, we'd be setting this equal to 0 because we wanted critical numbers. I don't want the critical numbers right now. I will later, when we do the second derivative test in the next lecture. But for now, we're supposed to find the second derivative. We're only talking about inflection points here. The derivative of 3x squared would be 6x. The derivative of plus 6x would be plus 6. The derivative of 9 is 0, just like the derivative of 13 is 0. Now we're supposed to be finding inflection points, so we set this equal to 0. We just said that inflection points occur when the second derivative is 0 and it switches concavity. So not only are we going to have to find where the x value is that makes this 0, we're going to have to do test points to see what happens to the left and to the right to see whether it switches or not. This is super easy to solve when you get 0 equals 6x plus 6. Subtract 6 on both sides, you get negative 6 equals 6x. Divide both sides by 6 and you get negative 1 equals x. So this is our potential inflection point. It's possible. We don't know until we do a test point process. Excuse me. So here's our negative 1. That's our possible inflection point. And if you want to abbreviate that PIP, possible inflection point, you can. But I'm just going to label our test points to the left and the right. So a test point of a number to the left of negative 1, maybe negative 2. And to the right of negative 1, maybe 0. Those would be good. So we're going to plug those into the second derivative, not the function, not the first derivative, the second derivative. Because we're checking concavity. All right, so f double prime of negative 2, that's just 6x plus 6. So 6 times negative 2 plus 6, that's negative 12 plus 6, which is negative 6. Therefore, it's concave down. So in that region, in this negative 2 region, it should be a downward facing parabola. And once again, I did not give myself enough room. Someone told me I can move stuff, but it always moves really funny like that. I can't ever just get a small region to move. So that's kind of unfortunate, but it is what it is. So in that region, it's concave down. Again, in that region, it looks like this. In the region of the negative 2, when it gets to the negative 1, it might be changing. It might continue that, it might change. So let's find out what happens to the right. F double prime of 0, that's 6 times 0 plus 6. Well, that's 0 plus 6, and that's positive 6. Positive means it's concave up. So in that region, it looks like an upward facing parabola. So here is the point, wherever that point is, I don't know exactly the height, but here's the -1. To the left of it, it looks concave down. To the left of it, it looks concave down. So again, this is not, I'm not drawing this. This is not what I'm drawing. To the left of this point, it looks concave down. So it should look like this to the left of that point. Because we are concave down to the left of the -1, where the -2 is, where the -3 is, where the -5 is, and the -1,000,000 is. To the right of it, in fact, let me switch colors. Let me just do this with like a green for emphasis. So to the right of that point, it should be concave up. So it went from concave down to concave up. It switched, therefore, -1 is an inflection point. So because, no underlining, cavity switched at x equals -1. It's an inflection point. I'm just going to abbreviate it because I'm going to run out of room. Because the concavity switched at x equals -1, it is an inflection point because the second derivative was 0 there, as well as it switched concavity. I didn't actually have to draw this image to see that. It went from concave down on the left to concave up on the right because you see these are two different things. That was good enough. This picture was just, again, giving you better an idea of what it would look like. In fact, you can draw some ideas about some extrema here, some relative extrema, and whether they'd be relative maxes or relative mins, just based on the concavity. And that's what we'll talk about next class. But we're going to go.
And of course, by next class, I mean, in just a minute, just give me a second to set up the continuation of that. And it'll be about the last 22 minutes of class, where we're going to talk about something called the second derivative test.
In 3.2, we talked about the second, or we are talking about the second derivative test, but we haven't gotten to that yet. So far, we've mainly just talked about concavity. So concavity is related to the second derivative, and if your second derivative is positive, it means you're concave up. If your second derivative is negative, it means you're concave down. And this is what a section that's concave up or concave down looks like. It means you're bending up or bending down as you continue to move to the right. And then here's us saying what I just said out loud. If the second derivative is positive, concave up. If the second derivative is negative, it's concave down. Now, you're only finding this out at certain points. You're not saying it's concave up everywhere, concave down everywhere. It's possible. But a lot of these functions will be concave up in one region and concave down in another region. Or concave up in several regions and concave down maybe nowhere potentially. That is possible. It's weird, but it's possible. So when you're in a region that looks concave up, you're shaped like this. When you're in a region that's concave down, you're shaped like this. So what the second derivative test is centered around is that you find your critical numbers. You find where your first derivative is 0. So if you find where your first derivative is 0, it's likely this point or this point. It's very likely to be one of these points. So what you then do is you go to the second derivative and you actually plug in the critical number. And if that critical number is positive on the second derivative, it's concave up, which means that point has to be a min. Or if the second derivative of a critical number is negative, that means we're here and it has to be a max. So the second derivative is similar to the first derivative test, but it also is a little different. The first derivative test, we were plugging test points in. In the second derivative test, we're actually going to plug the critical numbers in, because all around that critical number, the concavity should be the same in that local region. So you don't have to do test points. And in fact, if you take a test point too far out, that test point doesn't prove anything necessarily. So that's the main difference between the first and second derivative test. Instead of plugging in test points, you're plugging in the critical numbers, but into the second derivative. You're not going to plug them into the first derivative because you know it'll spit out 0. So the other thing we talked about was inflection points. This is where the concavity changed. We showed what that tends to look like. And we found inflection points and where it was concave up and concave down by doing a test point approach on the second derivative. That's not what I was just describing a few minutes ago. So when you're checking concavity or when you're trying to find inflection points, this is the same as the first derivative test, but under the second derivative test. But under the second derivative, excuse me. You do have test points to find concavity. But when you want to do the second derivative to find maxes and mins, you use the critical number instead. So that's the major difference there. And you've got to make sure you're practicing on your homeworks, because if you don't practice, when you get your test, you're likely to do the test points instead of the critical numbers or vice versa under the second derivative. Now, all the things I said earlier, I'm of course going to write on the screen right now. So here is our second derivative test. So first, the first derivative. And then set it equal to 0 and or undefined if you've got a non-polynomial function. Find its critical numbers. Then second, we find the second derivative. Then you will plug in the critical numbers, not test points, not test points, not test points. You will actually plug in the critical numbers into the second derivative. If you plug it into the first, you're going to get 0 or undefined every time. It's not going to tell you anything. If this value is positive, it means the function is concave up in that region and thus a local min. Not enter, there we go. If this value is negative, it means the function is concave down in that region and thus a local max. Again, the picture says 1,000 words. You find your first derivative, then you find your critical numbers. At the critical numbers, those are potential extrema. Then you find the second derivative. So if you have a point, here's your critical number. Now you know at this critical number, if it's a max or a min, it's going to look like this, or it's going to look like that, one or the other. It either has to be going down, or it has to be going up if it's an extrema. Like I said, it's possible they go in different directions, but if it's an extrema, that's what happens. That's what we anticipate. So we know that would happen at the critical number potentially. When we go to the second derivative, we just plug this in to find its concavity. So if we plug the critical number in and we get 7, that means the function is concave up around the critical number. Well, a critical number has the 0 derivative, which means it has to look like this. If you're concave up at the critical number, it has to look like this so that your tangent line is horizontal. Well, if you're concave up, that means it has to be a min. Conversely, if you plug the critical number into the second derivative and you get, say, -5, that means you're concave down at the critical number. But the only way to be concave down on a critical number is to look like this. That way its tangent line is, again, zero slope. It's horizontal. So if we're concave down around a critical number, that means it has to be a max. This feels backwards. I know it feels backwards because you get, if you plug it in and you get a positive value, it's a min, and a negative value, it's a max. That feels backwards. Guess what? In math, a lot of things feel backwards. We dealt with that a lot when we were shifting and reflecting graphs back in pre-calculus. We dealt with that a lot when we were trying to deal with the vertices of a parabola back in pre-calculus, like that x minus h scenario. Now, on a test, on an actual test, if the problem says to use the first derivative test, your work needs to show the first derivative test. If the problem says use the second derivative test, you get the idea, your work should show the second derivative test. If you get the answer right on a test, and then I go back and look at your work, and you don't follow the instructions they request, I reserve the right to dock some or all of your points. And admittedly, I won't dock all, it would be some. I think at worst, I'd give you half credit, and I'd probably even be a little more generous than that. But following instructions is important. Now, I am 99% of the time all about if you can get an answer right every time, why does it matter how you got the answer as long as it's consistent? The reason I say that for these is, first of all, some of the problems where they ask you to use the first derivative test, if you go to the second derivative test, it could be inconclusive, or it could be really, really, really hard. And some of the problems that are supposed to use the second derivative test, once again, it could be, I don't want to say it would be more difficult to use the first derivative test. That's pretty rare, but it could be a bigger pain in the butt. It could be more time consuming. There are times when the first derivative test is better. There are times when the second derivative test is better. And how do you know when they're better? By practice. I can tell you when it's better. Certain types of polynomials, it's better just to do the first derivative test or the second derivative test. If you've got a product or a quotient, the first derivative test is probably easier because if you got to take a second derivative of a quotient, that's two quotient rules. Doesn't sound like a good idea to me. Same for a product. But if it's a straight up polynomial, first derivative test is usually fine. But again, there are times when a second derivative test can be inconclusive. There are times when a first derivative test can be inconclusive. So you need to follow given instructions. Once again, I reserve the right to take away points if you don't follow instructions with this. I didn't really do any of that in test one. I can't really think of a scenario in test three where that will be the case, but you must in this instance. All right, rant aside, which I know we all love Mr. Beckner's rants, let's try this out. Example one. So we are going to find all relative extrema by the second derivative test. And we'll have the function x cubed plus 3x squared plus 3x plus 6. That's our original function. So we want to find the local extrema. We want to find the highs and the lows in local or relative areas. So we got to find the first derivative. 3x squared plus 6x plus 3. Okay, so we take this and we set it equal to 0 to find the critical numbers. If this was a fraction, we'd set the top and bottom equal to 0 to find critical numbers. So we go 0 equals 3x squared plus 6x plus 3. And we got a factor. Pop a 3 out as a GCF. You get x squared plus 2x plus 1. Factor pairs of 1 that multiply to 1 but add to 2 are 1 and 1. So we go 0 equals 3 parentheses x1, x1. And all these are positives, so all these are positives. Again, 10 million times I've said it, you've got to know how to factor. Now the x plus 1 and x plus 1 are the same, so they're not going to lead to different answers. I'll show all three equations, but you get 3 equals 0, which is trash. We've seen something like that before. Throw it away. We get x plus 1 equals 0 and x plus 1 equals 0. Subtract 1 on both of those and you get x equals negative 1. 2 times. Those are our critical numbers. Well, critical number singular since we only found 1 twice. Now, when we talk about the multiplicity of a 0 in a regular function, that talked about whether it bounced or crossed, so it gave something unique. Maybe when a critical number repeats, maybe that has something to do potentially, and I'm not going to say explicitly, but maybe that has something to do with extrema as well. I don't want to spoil too much though. So if this was the first derivative test, we only have the -1 up there. We draw a -1. So again, I'm going to write some stuff up and then erase it. If this was the first derivative test, we have our number line with the -1 as our critical number, and then we'd use -2 as a test point, and we'd use 0 as a test point. But we're not doing the first derivative test for now. We were told to do the second derivative test. So what that means is we need to erase all that. There we go. And we're supposed to take the second derivative. Once we have our critical numbers, take the second derivative. Hold on a second. What's going on? Okay, sorry about that. So now let's take the second derivative. I'll do that in blue. So f double prime of x. So let's go back to before it was factored, because why would you want to use a product rule if you have a version where you don't have to use the product rule? So we'll take the 2 out in front, so that'll be a 6x. The derivative of a plus 6x is just a plus 6, and the derivative of 3 is 0. I'm going to say this again. You have got to be the kings and queens of your power rules. You need to know your product rules and your quotient rules inside out as well as your exponential and log rules. But the power rule is the one you see the most. You cannot pass this class without your power rules. A student could arguably pass not knowing maybe one of those other things. You need to know some. You can miss one and still pass with like a B or a C, but you ain't gonna get an A. Okay, now, if we were finding concavity, we would set this equal to 0. So I'm just going to go back to it for a second, just as a reminder. If we were talking about concavity, just concavity, not extrema. We were just talking about concavity. That's where we set the derivative 0 and then did the test points around it. That's not what's happening here. I did not ask for concavity. So I'm not setting this equal to 0. We now plug the critical numbers into f double prime to see how the concavity is at those numbers. So we'll do f double prime of -1, which is 6 times -1 plus 6, which is -6 plus 6, which is 0. What? So that means it's not concave up or down at the critical number. What this means is inconclusive. Well, that sucks. I just told you to do a problem by the second derivative test and I came up with something that was inconclusive. I bet you I did that intentionally. I bet that has to do with the thing I was saying earlier about your test problems where if it says to do it one way, you should do it that way. Okay. So if this is inconclusive, what you should do is try the other test. Since the second derivative test was inconclusive, try the first derivative test. So that thing I had earlier in black, that's what we're going to do. And we're going back to the first derivative, so I'll do it in red. Okay, so we have our number line. Well, yeah, number line. The only critical number we had was the -1, so that's our critical number. We'll use the -2 as a test point and the 0 as a test point. So we're going to do f prime of -2. Remember, it's easiest to plug it into a factored form if you have it, and just do the signs. So 3 times -2 plus 1 times -2 plus 1, which is a positive, times a negative, which is a positive. So that says it's not concave up. Remember, second derivatives, concavity. First derivatives, increasing or decreasing. That says it is increasing in the region of the -2. So in the region of the -2, it's going up until we hit the critical number. Now let's try what happens to the right of the critical number. So f prime of 0. That's 3 times 0 plus 1 times 0 plus 1, which is a positive times a positive times a positive, which is a positive, and it's increasing again. We have not seen that happen yet. So in the region to the right of the -1, it's going up again. So I feel like we tend to draw it that way, so maybe keep drawing it that way. And if that's a little weird to you, instead of having it disconnected, let's do it this way. So we're going up until we hit the -1. So here's the -1. And then we're going up again. And it probably doesn't do that. It probably bends the other way. And I say probably because it's possible that it bends the other way, but this is increasing on the left, and then this is increasing on the right. This is not a max. This is not a min. This is what's known as a saddle point. A saddle point is a critical number that is not an extrema. It's saddled between two different sections of being increasing. So this problem has no extrema. If you don't believe me, graphing calculator. Go to the graph screen. What was our original function? X cubed plus 3x squared plus 3x plus 6. Go to graph. And look at that. Here's our -1 if I hit trace. -1. There's the critical number. You can see that the derivative is 0 there because a tangent line would be horizontal. Let me zoom in on that point just to make that a little more clear. Look at that. So we're increasing, we flatten out to 0, but then instead of turning back around, it has more of a cubic function look, and it keeps on increasing. This is possible. And guess what? This has everything to do with the fact that there's a multiplicity in the critical numbers, and that the multiplicity is even. So this is what a saddle point looks like. It's when we go increasing and then increasing, or vice versa, decreasing and then decreasing again. So it's not a max, it's not a min. It's neither. So there were no extrema of this problem. Now, very often, when you see the scenario, the second derivative test is going to fail because the concavity here is 0. Because if you look left, let me throw the annotate on and just kind of draw over my calculator. To the left, if you kind of ignore what's happening here, this is concave down, so you'd think it would keep doing that. But then to the right, it's concave up. So we are actually switching concavities there immediately from down to up. Those parts just don't exist. So we went from concave down to 0 concavity and then concave up. So because the concavity was 0 at that point, you can't tell whether it's facing up or down, and that's because it was neither. It's kind of like joining both of them together. Gonna have a hard time finding that problem because I didn't grab the page. Let me just do this. This will be easier. So what you might think is that the second derivative test is bogus. Let's actually pull a problem we've done before.
And that's what we'll do next time so that we can have some compare and contrast kind of situation. All right, but just reminding you of our due dates. In the last minute, we have a class, last minute and a half. 1.7, 1.8 due tonight, 2.2, 2.3, due in a week. Test 1 now due on the 24th. Just giving you one extra day for this first run. Next time it will be a 3-day window. Make sure you show your work. Make sure you submit it in Canvas. Again, when you look in Canvas, you should see the class videos, and then immediately under the class videos, you should see a folder section, whatever you want to call it. And it'll say submit test 1 here. 20 questions, 2 hours, no notes, no books, no calculators, no funny business. No questions? Then we'll call it an evening. As always, if you do have any questions, you can email me. Remember to shoot me an email if you believe you deserve any partial credit. Make sure you say what questions, make sure you say what class you're in. Again, I do prefer those to go over Canvas just for organization reasons for my end, but you can still send it to rbackner@tcc.edu as well. All right, have a good week, everyone. Study hard, work hard, do well on the test.